something that feels a bit strange, almost contradictory to everyday experience.
Definitely.
How something like light, which seems so, well, weightless, can actually push things.
Yeah, it's a great topic.
You've sent in some really fascinating sources looking at photon momentum and this thing called radiation pressure.
That's right.
So our mission today is to unpack this, understand the physics behind how light pushes and look at some, frankly, pretty amazing implications.
And the core puzzle, right, the thing that jumps out from the sources is how? How can light, which we're always told is massless, have momentum? How can it exert a force?
Exactly. It just feels wrong somehow based on, classical physics.
It absolutely does. And that's what makes it interesting, right? It pushes against our intuition, which is mostly built on, well, big stuff we can see and touch.
Right. Apples falling, cars moving.
Exactly. But the sources are clear. Light does carry momentum, even without mass in that classical sense.
Yeah.
And when that momentum hits a surface and gets transferred.
It creates a force, a push.
Precisely.
Okay, so this core idea is radiation pressure. Can you break that down a bit more? What is it, fundamentally?
Think of it like a very, very gentle but constant shove. Any surface that light hits feels this tiny push.
Okay.
And the force over a certain area, that's what we call radiation pressure. And it all boils down to the fact that light, when you think of it as particles, photons, these photons have momentum.
Right, photons, little packets of light energy. But that's the sticking point again, isn't it? The zero mass thing? How can they have momentum? We all learned P equals mv in school.
Yep, momentum equals mass times velocity.
If m is 0, P should be 0.
And that works perfectly for, like you said, baseballs, planets, anything with rest mass. But photons are different. They have to travel at light speed, c, and they have 0 rest mass. Their momentum comes from somewhere else.
Quantum mechanics and relativity, I presume?
Exactly where the sources point us.
Right.
The rules change for light. There are specific formulas that describe this.
Okay, so what are these quantum formulas telling us?
Well, one really key relationship is that a photon's momentum, which we call P, is inversely proportional to its wavelength. The color of the light, essentially.
Right. Wavelength.
That's the one. The formula is P equals H divided by lambda. P equals H.
And H is Planck's constant, that super tiny number.
The very same. About 6.626 times 10 to the minus 34 joule seconds. It's fundamental to quantum physics.
So P equals H. If the wavelength lambda is smaller...
The momentum P is bigger. Shorter wavelengths mean higher momentum.
Ah, okay. So like a photon of blue light carries more momentum than a photon of red light because blue has a shorter wavelength.
Exactly right. And there's another related formula connecting momentum to energy. E.
Okay.
It's P equals E divided by C. P equals E, where C is the speed of light.
So momentum is also energy divided by the speed of light. It makes sense higher energy photons would have more push.
Precisely. Higher energy also means shorter wavelengths, so it all connects. They carry more momentum, deliver a bigger kick, even though they're all traveling at the same speed.
That's fascinating. So for photons, momentum isn't about mass. It's about their energy or their wavelength. Quantum properties.
It's a totally different way of looking at it.
Now, the sources also mention something important. How the light interacts with the surface matters. Absorption versus reflection.
Oh, absolutely. It makes a huge difference to the force experienced. It's
Yeah.
all about how that momentum gets transferred.
Okay, let's take absorption first. What happens there?
Absorption is pretty straightforward. Imagine the surface just catches the photon, like catching a ball, as one source suggested.
Okay.
The photon had momentum coming in, it hits the surface, gets absorbed, stops existing as a free photon, and its momentum is entirely transferred to the surface. The surface gains momentum P.
Simple. Photon stops, surface gets its momentum. Got it.
So what's different about reflection?
Ah, reflection. That's where it gets, well, doubly interesting, quite literally.
Doubly.
Yeah. If a photon hits a surface and is perfectly reflected, it doesn't just stop, it bounces back.
Great. So its direction changes completely. If it came in with momentum plus P, it leaves with momentum less P. It reversed its momentum.
And momentum has to be conserved. The total amount can't just change.
Exactly. So for the photon's momentum to go from plus P to match P, the surface has to provide the change. It has to absorb the incoming momentum plus P and provide the momentum needed to send it back out.
P. So the total change imparted to the surface is P minus negative P, which is 2P.
Precisely. The surface experiences a change in momentum of 2P, twice the momentum transfer compared to absorption.
Wow.
The analogy was like a ball bouncing off a wall. The wall feels a bigger impact than if the ball just splatted and stuck there.
So a perfect mirror gets hit twice as hard by light as a perfect black surface.
Under the same light intensity, yes. twice the force, and therefore twice the radiation pressure.
That's a really significant difference.
It is, and it's crucial, as the sources highlight, for concepts like solar sails.
Right, those giant space mirrors people talk about.
Exactly. You want them to be incredibly reflective, to maximize that push from sunlight, to get that 2p momentum transfer from every photon.
That double force effect is definitely a key takeaway. But, okay, we're talking about photons. A single photon's push must be unbelievably tiny. We don't feel the lamps in this room pushing us over.
Not at all. It's infinitesimal for one photon.
So how does it add up to anything measurable, like radiation pressure?
It's the sheer numbers. A typical light source, even a dim one, is pumping out trillions upon trillions of photons every single second.
Okay, yeah. A lot of tiny pushes.
An unimaginable number. Each photon gives a tiny nudge.
Yeah.
But when you have that constant barrage hitting a surface, the collective effect adds up. That's radiation pressure, the total force from all those photon impacts spread over an area.
And the sources gave formulas for this pressure, too, based on the light's intensity.
They did. Intensity, usually symbolized by I, is the power per unit area. How much light energy is hitting a square meter each second, essentially. Yeah. For a surface that absorbs perfectly, the pressure P is just the intensity divided by the speed of light. P equals I over C.
Okay.
But for that perfectly reflecting surface.
It's doubled, right, because of the 2p transfer.
Exactly. The pressure is P equals 2IC. Twice as much pressure for the same light intensity.
And I guess most real things are somewhere in between. They absorb some light and reflect some.
That's right. Real-world surfaces have reflectivities between 0 and 1, so the pressure they experience is somewhere between I and 2IC.
Are there examples where this pressure, even though small, actually matters?
Oh, definitely. The sources mention comet tails. One of a comet's tails, the dust tail, is partly formed by this gentle but relentless push from sunlight, pushing dust particles away from the sun.
Ah, interesting. So it always points away from the sun.
That part of the tail does, yeah. It's a visible effect of radiation pressure on a cosmic scale. And, of course, the futuristic propulsion ideas.
Solar sails again.
And maybe even more advanced light-based propulsion someday.
Okay, let's swing back to that fundamental point that seems tricky. The constant speed of light versus variable momentum.
Yes, the apparent paradox.
How can light always travel at c, this universal speed limit, if its momentum can change depending on, say, its color or energy? It feels like one of those things should affect the other.
It's a great question. And it really gets to the heart of how relativity and quantum mechanics work together. The sources clarify this beautifully. First, the speed of light.
C, constant for everyone, everywhere in a vacuum.
Exactly. That's a cornerstone of Einstein's special relativity. It's been tested like crazy and holds up. The speed is fixed.
Okay, speed is fixed, but momentum varies.
Yes, because a photon's momentum doesn't come from mass times velocity. Remember, its rest mass is 0. Its momentum comes from its quantum properties, its energy E or its wavelength.
Through P, EC, or P equals E?
Correct. So think about different types of light. An X-ray photon, for instance.
High energy, very short wavelength.
Right. According to P, LE, small e means.
Big P, lots of momentum.
Exactly. Now compare that to a radio wave photon.
Super low energy, really long wavelength.
So large bike means?
Small p, less momentum.
Right. But here's the crucial bit. Both that high momentum X-ray photon and that low momentum radio photon are traveling at exactly the same speed.
At c?
At c, always.
So the speed being constant and the momentum being variable aren't in conflict at all?
Not in the slightest. They are governed by different, though interconnected, principles. Speed c is fixed by relativity for light in a vacuum. Momentum p is determined by the photon's quantum nature, its energy or wavelength.
One describes how fast it goes, the other describes, well, almost like its punch or its energy content manifested as momentum.
That's a good way to think about it. A photon's momentum tells you about the kind of photon it is. High energy, low energy, not how fast it's moving, because they all move at the same speed. It's a beautiful interplay between relativity and quantum physics.
Okay, so wrapping this deep dive up, it feels like we've really uncovered something fundamental. Light does push.
It really does.
Because photons, despite being massless, carry momentum defined by their energy or wavelength.
Check.
And how much they push depends crucially on whether they're absorbed, momentum p transferred, or reflected, momentum 2p transferred.
That doubling effect from reflection is key.
Right. And while one photon's push is tiny, the sheer number of them adds up to a measurable force, radiation pressure, that depends on the light's intensity.
I for absorption, 2IC for reflection.
And finally, we reconciled the constant speed of light c with the variable momentum of photons. They aren't contradictory. Speed is fixed by relativity, while momentum reflects the photon's quantum energy.
Exactly. It's not PMV, it's PEC or PO for light.
This really does change how you think about light, doesn't it? It's not just illumination or heat, it's a physical force, too.
Absolutely. From shaping comet tails to maybe, one day, pushing spacecraft between stars using giant solar sails. The very idea that something without mass can carry momentum and exert force is, well, it's one of those wonderful reminders from quantum mechanics that the universe is stranger and more fascinating than our everyday intuition suggests.
It really makes you wonder, doesn't it? What other incredibly subtle forces, maybe just as counterintuitive as light pressure, are out there constantly shaping things on cosmic scales? Forces we're only just beginning to glimpse.
A fantastic thought to leave with. There's likely still so much we don't perceive directly.